All right, 5G radiation and temperature. The first thing that we're going to look at is basically an intensity with wavelength radiation curve. And this graph is the most common graph that you would see if you were given a question or you were looking at the radiation emitted by any object. So this curve essentially shows us, first of all, the y-axis, which says flux, which is just another word for intensity. So in this context, the amount of radiation that is emitted by an object. So the amount of radiation on the y-axis, and then the wavelength of radiation on the x-axis. Now, what we're saying in this section is all objects can or do emit radiation, but how much radiation they emit and what type of radiation they emit depends on their temperature. All right, and obviously the way that it depends on their temperature we're going to look at in this section. But essentially, not all objects emit all types of radiation, and not all objects emit a lot of radiation. So this curve essentially is saying, well, there is a peak. If you find the peak on each curve, you've got a blue and a yellow and a red. The peak on each curve is actually at different levels of intensity. So the blue one clearly emits the most amount of radiation. So the peak for the blue is much higher than the yellow. This one emits a little bit less radiation, and then the red, in this example, emits the least amount of radiation. Now, if you actually also look at where those peaks are, and you can see with the dotted lines from the very peak of each curve, it goes down to the x-axis, which in this case is wavelength in nanometers. But if you go down from the peak, you can see that they're at 3 different points. So the peak radiation for each of these colors or each of these curves is not at the same wavelength. Now, looking at the blue one, we said first of all that the blue curve emits the most radiation or more intense radiation, and the peak of this curve is at 400 nanometers. Now take a look at the yellow one. We said it emits less radiation or less intense radiation than the blue, and if we follow this peak down, the peak on this one is actually somewhere between 400 and 700 nanometers, so slightly bigger or longer wavelength than the blue one. And then looking finally at the red one again, this peak is the lowest peak, so the red line actually emits the least intense radiation or the least amount of radiation, and the peak for this specific curve, the wavelength at this peak is 700 nanometers, which is the longest wavelength of all 3. Now, simply looking at this and obviously having a look at the temperatures which are associated with each curve, so the blue line, it says here, is 18,000 Kelvin, which is the same, give or take 273 degrees, but it's the same as degrees Celsius for all intents and purposes. So around 18,000 degrees Celsius, 6,000 degrees Celsius, and 4,000 degrees Celsius. So they're changing in temperature. Red is the coldest, then you have yellow in the middle, and then blue is the hottest or the highest temperature of all 3. But if we compare the temperature to the amount of radiation emitted by these objects, then the higher the temperature, the more intense radiation emitted. So first of all, for radiation and temperature, this is absolutely key. The higher the temperature of an object, the more intense radiation the object emits, which just means the higher the temperature, the more radiation is emitted by the object. Secondly, we can see that the higher the temperature of the object, the shorter the wavelength emitted at the peak. Because obviously this curve actually suggests that this object doesn't just emit one type of wave. It doesn't only emit radiation at 400 nanometers. It emits radiation actually across a large range of different wavelengths. However, the wavelength that this object emits the most is at 400 nanometers. So the second thing we said about objects and their temperature, the higher the temperature, the more intense radiation. And secondly, the higher the temperature, the shorter the wavelength at the peak. Okay, so the lowest temperature, 4,000 on the red line, the least intense radiation emitted, and the longest wavelength. Okay, higher temperature, shorter wavelength emitted at the peak, more intense radiation. Lower temperature, longer wavelength, and less intense radiation. Now, what does that mean in real life? How might I experience that in everyday life? One example is actually looking at the temperatures of different stars and how they appear. So orange star, such as the sun, we see the sun, it looks like a yellowy orange star. Red star, which might be a red giant star or red supergiant, and then blue stars, which actually, if you look quite carefully on a clear night, you can see that some stars look quite blue. Instead of white, they look quite blue. So we have 3 different colored stars, and we're trying to determine essentially what might the difference in temperatures be between these 3 stars. Now, generally most people think red is the hottest color because it's red hot, but that's not necessarily true. Other people might say, well, actually the blue flame on a Bunsen burner flame, the blue part is the hottest part, and that is more correct actually than the red hot star. Now, what is going on in terms of the physics and the temperature with wavelength that we just discussed? Well, we said the higher the temperature of the object, the shorter the wavelength. Now, if we're just talking about the visible spectrum, red, orange, yellow, green, blue, indigo, violet, red has the longest wavelength and violet has the shortest, where blue is closer to the violet. Now, if red has the longest wavelength and blue to violet is the shortest, we said the higher the temperature, the shorter the wavelength. Now, blue, of the 3 colors, blue has the shortest wavelength, which must suggest that this star is actually the highest temperature. Red, on the other hand, actually has the longest wavelength of all colors in the visible spectrum, so red therefore must have the lowest temperature. Orange yellow obviously is somewhere in between the wavelengths, and therefore the temperature of this star would be in between the 2. So red is the lowest temperature, which has the longest wavelength. Blue is the highest temperature because it is emitting the shortest wavelength of visible light. All right, the next thing that we're going to look at is objects that emit and absorb radiation. They can emit and absorb different amounts. All right, now if we look at the polar bear, for example, what we're saying is the power of an object. Now, the power is essentially just saying the amount of energy that this object absorbs per second, or the amount of energy that this object emits per second. So the power is just energy per second. Now, if the power of an object absorbed per second is exactly the same as the power that is emitted by that object per second, so the absorption of energy is equal to the emission, then that object's temperature remains constant. Okay, so an object will remain at constant temperature if it absorbs the same energy as it emits per second. Take the polar bear, for example. It says this polar bear is absorbing 20 kilojoules in 10 seconds. So 20,000 joules in 10 seconds, but it's emitting 50,000 joules in the same 10 seconds. So in this specific example, they are not equal. The amount absorbed in 10 seconds is not the same as the amount emitted in 10 seconds. So what's happening to the polar bear if it is emitting more than it's absorbing? It's not at constant temperature because we said that has to be equal. So in this case, if you give out more than you take in, then you are cooling down. Your temperature will decrease. If you absorb more than you give out, so for example, you absorb more than you emit, then your temperature will increase. So there are 3 different things that can happen in terms of the absorption of energy per second and the emission of energy per second. If the power absorbed equals the power emitted, then the temperature of the object remains constant. If the object absorbs, takes in, more than the object emits per second, then the temperature of the object increases. And finally, if the object emits more energy than it absorbs, so it absorbs less than it emits per second, then the temperature of the object decreases. So there are 3 things that can happen to any object. Now, one quite common example actually asked in the GCSE exam is of a light bulb. It doesn't have to be a polar bear. It doesn't even have to be the Earth, which is what we need to look at in this section, so the temperature of the Earth itself. But a light bulb, when a light bulb is switched on, the temperature initially increases. Now all you need to think about there is, well, if the temperature is increasing, that means the light bulb itself is absorbing more energy than it's emitting at that time. But then when the temperature is increased, it reaches a maximum constant value, so the temperature of the light bulb actually then remains a constant value, which means now the light bulb is absorbing exactly the same as it's emitting every second. All right? If the light bulb were then to drop and decrease in temperature, what that would mean is that the light bulb is now actually emitting more than it's absorbing. And that can be used in any situation. Now, if we take a look at the Earth specifically, the temperature of the Earth is very common knowledge actually on the planet today that the Earth's temperature is increasing. Global warming is a thing. The Earth is warming up. But let's look at why and what's happening. Now this is an image of what should be happening. Every single day we take in energy from the sun, so we absorb our radiation from the sun. Different parts of the atmosphere, clouds and the surface, take different amounts and different parts, but we don't need to look at that specifically. But we absorb our infrared radiation as well as our light and other things. But infrared radiation, which is the temperature and the heat energy absorbed by the Earth every single day. Now, what should be happening is we should be giving back that energy at the end of a day, for example. We should be giving back that infrared radiation through the clouds, through the atmosphere and back into space, so that what we absorb is equal to what we emit. Because if what we absorb equals what we emit, then the temperature of the Earth will maintain a constant, healthy temperature. Now, the problem is, what we're saying is, over time, we're still absorbing the same amount from the sun, so we're still taking in the same amount, but we're not emitting, so we're not giving back the same amount every single time. We're giving back less. So what's happening is we're absorbing more, we're emitting less, and therefore the temperature of the Earth overall is increasing slowly. This is happening over years and years, but the temperature overall is gradually increasing. Now, first of all, reasons why are we giving back less? Why are we taking in more and giving back less all the time? Greenhouse gas, or greenhouse gases, are the most important, or the key factors for why we're absorbing more radiation than we're giving back or than we're emitting. And examples of greenhouse gases are carbon dioxide, water vapor, methane, nitrous oxide, other things as well, but those are the main ones. And what's happening is we're actually putting those gases into the atmosphere. For example, CO2, carbon dioxide, we're putting those in the atmosphere because we're using power stations that produce CO2. And those CO2 atoms are obviously going into the atmosphere, and therefore they are absorbing infrared radiation, which means we're giving back less. All the other things that we're adding to the atmosphere that absorb infrared radiation mean that we're giving back less than we're taking in. So the temperature of the Earth is going up. So greenhouse gases are the problem. We're personally adding those to the atmosphere because they absorb infrared, we give back less. All right? What's going to happen eventually, though, in the future is as the temperature continually increases and we keep taking in more than we're giving back, eventually, just like the light bulb actually in the example, the temperature will reach a new constant temperature. So eventually we're going to start taking in as much as we're giving back. But unfortunately, we will have reached a new higher temperature, which might actually be very dangerous to the weather on the Earth, the different habitats around the planet. Different countries may experience different things. So that new temperature will have been reached, and then we're at a new balanced temperature. In fact, it will be very hard to go back to a healthy temperature once the increase has happened and we've reached that new constant temperature. So we have to be very careful with the amount of pollutants and the greenhouse gases that we're constantly putting in to our atmosphere. One more thing to point out. If we look at different objects and the amounts and type of radiation that can be emitted by those objects, going back to the two things, the higher the temperature, the more intense radiation, and the higher the temperature, the shorter the wavelength emitted at the peak, then we can actually take a look and say, well, what objects or which objects will emit which types of radiation? Starting in terms of the temperatures, you have the sun, a polar bear, a hot cup of tea, and a table. If we order these from highest to lowest temperature, we'd say the sun is probably the highest temperature. If it's a brand new hot cup of coffee or tea, it might be at around 80 degrees Celsius. So then this one would be higher temperature. Polar bear, internal temperature similar to the human body, maybe 38 degrees. And then a table which is at room temperature of 23 degrees. So sun, coffee, polar bear, table from highest to lowest temperature. Let's discuss what they might be emitting. Now, the sun is the highest temperature, which means it can emit the most intense radiation. The table will be emitting the least intense radiation. So highest temperature, most radiation. Lowest temperature, least radiation. And then we can also say for the sun that the highest temperature must be emitting the shortest wavelength. Now, before we only consider the visible spectrum, most objects emit infrared radiation. Infrared on the EM spectrum has longer wavelength than visible light. So if an object is actually able to emit visible light, that must mean that the temperature is high enough that the wavelength became so short that it is moving from infrared to visible light. So because visible light has a shorter wavelength than infrared, any object that can emit visible light when its temperature rises is because the wavelength is getting shorter and shorter. In fact, the temperature for an object to emit visible light is around 800 degrees Celsius. So almost every normal object, everyday object, even boiling water at 100 degrees Celsius cannot emit visible light because the temperature is not high enough, therefore the wavelength isn't short enough. So it emits infrared heat, thermal radiation, but the wavelength is not short enough to move into that visible spectrum. The temperature has to go higher to around 800 for the wavelength to come short enough to reach the visible spectrum. Now, stars are so hot, we're talking temperatures as before, up to 18,000 degrees Celsius, in which case the wavelength that these stars can emit will keep going shorter and shorter. So they will be able to emit visible light, which is shorter than infrared. Even higher temperatures, they'll be able to emit ultraviolet with even shorter wavelengths. And then if their temperatures go higher and higher, they can emit X-rays and all the way to gamma rays. The shortest wavelength EM waves, the temperature is high enough, it can emit gamma rays. And stars do that. But at the peak, it's probably emitting in the visible light. It still can emit those shorter wavelengths because it does have the temperature, but the peak will probably be in the visible spectrum maybe, or maybe in the UV or different parts. But most everyday objects, their temperatures are not high enough so that the wavelength of radiation they emit is not short enough to go into visible light. So all of these objects can only emit infrared radiation. So just bear that in mind when they're asking about the types of radiation that different objects can actually emit. It's about the temperature and therefore the wavelength. All right?